Yay. Welcome back, you crazy people. I will say, Calc 2 is the hardest. This is going to be easy, except that quite frequently we're going to run into a problem where we're doing, all of a sudden, one of those crazy integrals from Calc 2 comes up. One of those crazy substitutions is needed. Those pieces become what we use here, ideally less often, but we'll do a bunch of stuff in polar, we'll do a bunch of stuff in parametric equations. We're going to need all those pieces. But most of the actual calculus we're going to do is going to look like Calc 1 again. The difference? We're in 3D now. More variables. Let's figure out what the hell everything means if we're really dealing in a 3D universe. 99% of all of this stuff is crap you've seen before. Office hours are Monday, Wednesday, Friday afternoon, Tuesday, Thursday, Tuesday longer than Thursday. Unfortunately, tomorrow I have a pair of interviews for a search committee I'm on. I will cancel my office hours. I'll jump back on that Google link that evening. You'll get an email about this like I did last semester where I had to cancel office hours. I'll be available tomorrow night, sitting at home, grading papers or not grading papers, because I don't think I will have collected anything by then. But you'll be able to get to me there. I am of the opinion that of all of the pieces of calculus we can do, the stuff we do at the end of this semester is absolutely amazingly beautiful, elegant, and deeply, deeply useful. But I was a physical chemist before I started being a math geek. So to me, this is chemistry. There's physics in here. There's so much actual practical utility in Calc 3 that it is emotionally fulfilling to teach. So I'm going to have a great time, and I hope you'll join me on it. Doing a lot of the same stuff. Vector calculus is how this is typically referred to, which means we're going to do a lot of stuff in vectors. Well, that means I've got to reinterpret all of that stuff in vectors. And we've got to understand how to do integrals and derivatives and limits and all that stuff in vector terms. What does that mean? It means more of the same, literally, but just more of it. Same spiel. Come to class. Coming to class helps. There are only 5 of you. This is it. I'm not missing anybody. But that means if you're not getting it, stop me. We're going to use the same tech, the graphing calculator again. There are some very good 3D graphing apps. The grapher built into the MacBook will be very helpful here. I'll show you and demonstrate in places where we're going to use it. I've got a whole bunch of already existing examples for you to work with as well. Just like last semester, we'll have a weekly submitted assignment. The assignment list is already up on Canvas, PDF file. Sample problems. In this case, I am grading the whole thing. I'm not just pulling a problem. So I will be grading the entire thing. 4 scheduled exams. Exams are on the course schedule. Let's see. Exam 1 is 3 weeks. February 10th. Chapter 12 in the first section of chapter 13. Please note there is a day we are missing. There will be a math competition here on campus for the middle school students in Westmoreland County. I would love to have some of you come along and help me for the day. You'll get an email about that coming up. And once again, we got screwed. Finals at 8. The final exam is a little more heavy than it is in some of the other classes, but comparatively, I still think that's a pretty good setup. There's the grading scale. 99% of the rest of this is the same crap you saw last semester. If you've got questions, come bug me. If you're sick, stay home. This is working, so hopefully my recordings will be fine. We'll keep our fingers crossed. In that case, we'll not even bother. please read the rest of this. And if you've got questions, come bug me. So let me start with the first problem. I want to work in 3D. And the first problem with that is that I'm working on a sheet of paper. Even if you're taking notes on your iPad or on your computer, you're seeing flat. So how do I figure out how to make 3D coordinate systems? Hopefully you've seen this idea already, but I'm going to assume not, and we're going to go from there. Here's our Cartesian plane, right? An x-axis and a y-axis. I didn't label it because I'm not going to. I want to make a change before I label it. I need a third dimension here. Where should I put that third dimension? It should come out at you, so I should do that. Right? That's atrocious looking. And besides, I don't know if all of you carry a pen or a pencil that'll balance perfectly on its end like this. I'm not going to do that. But notice that we're not looking straight down at this. This is not directly under the center of the camera. The center of the camera is about here. So it's offset a little and it looks a little tilted. And the further we move, the more tilted it looks, right? So let's change the perspective of this. And we'll add a third axis coming out at us. But we'll screw it up and draw it flat at an angle. Now, that looks wrong. Because it's flat, it doesn't look like a right angle anymore. But I still want to think of it like it's a right angle. So I'm going to label this, and the one that's coming straight out at us is going to be the x-axis. So I have x here, y here. That means that the Cartesian plane is the floor, x and y. And then the z-axis is up. We call this a right-handed system. I want you to picture a little person standing at the origin here. I'll go stand in the corner. I am standing at the origin. And now I have my right hand pointed out at you. My left hand in the y direction. And the z-axis runs up through my body. So this is a right-handed system because if you put a person at the origin, their right hand is the x direction. But it's also a right-handed system because I can use my right hand. Point at me. That's the x direction. Stick your second finger out. That's the y direction. Stick your thumb up. There's the z direction. You carry this with you everywhere you go. And we're going to see that the right-handedness of this system is also utilized in our physical world. The world is handed. And more of the rules for things in physics and chemistry work on our right than on our left. It's easy to tell who makes this mistake because in order to make your left hand line up the right way, you have to be rude about it, so don't do that. But there's our right-handed system. Now you can also think of it, instead of using your second fingers, to curl your fingers around, and then the palm of your hand is the y direction. So you have x where your fingers are, z where your thumb is, and your palm being the y direction. Again, right-handedness. Okay. There's a picture in the text on page, I wrote it down, but I think this is for the wrong edition of the textbook. (792). There's our hand. First finger in the X direction, second finger, we curl around. Okay. When we did the Cartesian plane, we had quadrants, right? Quadrant 1, 2, 3, 4, as we went around. What do I have here? I've got spaces instead, right? So let's think about the walls. Remember, I put myself in the corner over there. The wall here at the front of the room is the surface that goes through Y and Z. So this is the YZ plane. And then the XY plane is the floor. And the XZ plane, based on putting me in the corner, what wall would that be? It'd be the wall with the windows on it. Okay, but it's actually the entire wall, and the one at the front of the room should go out and hang out in the outside of the building there, right? And the XY plane should go out through the walls as well. So really, if we extend these outside this room, then we've divided our three-dimensional space into regions. Just like we had the quadrants on the plane, I'm going to think of this room as the first piece. If you're standing in this room, you have a positive X value, a positive Y value, and a positive Z value. So this piece of space is my first piece. Let's stick with that. Up here. I'm going to do the quadrants, right? This is 1. Quadrant 2. Quadrant 2 is negative X values, the positive Y values, right? Well, negative X values would be behind, wouldn't it? Positive Y values would still be on this side of the wall. So the second quadrant should be the room behind me, Mara 332, on the other side of this wall. The third quadrant would be back there, but outside the building. And the fourth quadrant would be on the other side of the windows, right here. So 1, 2, 3, 4. Just like we were looking down at the XY plane. But all of those had positive Z's, right? What happens if we go downstairs? I get another 4. I get 5, 6, 7, 8. So instead of quadrants, we have octants. So 1 and 2 and 3 and 4 are on the top going around, and 5 and 6 and 7 and 8 are on the bottom going around. And again, X, Y, Z. So we go around the plane, the XY plane, just like we did. If we looked down from the top, okay, so now I got to go back and I got to look down from the top. So I put in continue. If I look down from here, there's my eyeball looking down from the top. It's a horrible eyeball. It looks like an angle. Here's my eyeball. Then if I look down, I see X and Y like that. X points out at you, Y points to the left, quote unquote. But then here's 1, 2, 3, 4. Turn your head sideways. Oh yeah, 1, 2, 3, 4. I'm going counterclockwise around, aren't I? Now, underneath those are 5, 6, 7, and 8, the octants. Questions? To a lot of people, this is the hardest part of Calc 3. Figuring out how we're going to do math in 3D. Figuring out how to see what we drew as graphs aren't going to work the same way anymore, right? What we thought of as a function isn't going to look the same, because now I got to work in this. Questions? Talk to me. Points. How do you define a point on the Cartesian plane? Perfect. I need coordinates. How do I define in Cartesian space? I need another coordinate. I'm going to do the exact same measurement. I'm going to measure along the x-axis, measure along the y-axis, and measure along the z-axis. So if I have a point, where is it? The point 235. Here's my Cartesian space axes, my three-dimensional axes. Where do I put this point? Careful. I don't have quadrants anymore. I have octants. 4 above and 4 below gives me 8. Change the prefix. So yeah, it's definitely going to be in the first octant because all three numbers are positive. But let's physically map it out. I don't know what the units are. Feet, inches, miles, it doesn't matter. But I've got to go 2 units along the x-axis. I've got to go 3 units along the y-axis. And I've got to go 5 units along the z-axis. There we go. So I have 2 here and 3 here and 5 here. Now here's where things get interesting. I need to do 2 of these. I need to do these in order. So pick one to do first, then pick another one, and then pick a third one, right? So we can do it in any order we want. I'm going to do it backwards. I'm going to do z, y, x, because I think that helps. If I were to go along the z first, I'd be up here at this spot, right? The coordinates for this spot are 0, 0, 5. I'm on the z-axis, 5 units up. Then I'm going to go in the y direction. I'm going to go 3 units. 1, 2, 3. This is the point 0, 3, 5. Notice, just like I was in x and y, right? I just did it in y and z because that's flat on the paper. It's x that's out. This is where I get weird. I need to go 2 units this way. but my x-axis is tilted. So I don't go straight out. If I went straight out, you wouldn't see anything. It wouldn't change, would it? But I need to go parallel to the x-axis. So the motion in this direction has to be parallel here. 1 unit, 2 units. And that's the point 2, 3, 5. Now I didn't have to do it z, y, x. I could do it in any order. But I liked that one because I was able to draw the hardest part last. Part that goes parallel to the twisted axis. But notice, if I had gone x first and then y, I'd go from here, I'd go over 3 units, right? But I'm starting further to the left than I would be up here. That means that I have to end further to the left. 1, 2, 3. Similarly, I could have gone out 2 and then up 5, but since I'm starting from a position that looks lower, I'm going to have to finish lower. And look, I made a box. A bunch of the corners on this box have not been labeled. Let's go back and label all the other corners. So this is the point 235 right here. What's this point down here?
0.05.
5 would be up the z-axis, wouldn't it? Is this up the z-axis? It's still at the same height as flat on the floor, right? So this is the point 200. The point 205 is up here. What's this point?
0.30.
Aha. And that means that this point above it is 0.35. And then what's this point?
2.30.
Because it's still on the floor. Oh, and this one in the middle here, that's the origin, 0. I built a box. 2 units in depth, length, 3 units in width, and 5 units in height. And what we actually want is the outer corner. That is our point. But that means I could do this for points that are positive, be in the first octant. A point that had a negative x would be in the second octant behind me, back here somewhere. A point with a negative y would be over here somewhere. Points with negative z's would float down here. This is perspective, and I'm about to mess with your heads. Because one of the big pieces in art is the problem of trying to represent 3 dimensions in 2. A gentleman by the name of Necker came up with the drawing of a cube. Ready? I want you to look at the cube. This is the front. The cube points this way. No, this is the front. The cube points this way. If you stare at it long enough, it switches back and forth in your head. It's called the Necker cube illusion. And it comes down to these 2 problems. I don't know which line is in front and which line is behind. I can change that by physically breaking the sides. Now it's clearer which one's in front, yes? But I could switch them and draw it the other way. This is the difference between being an art major and a math major. Because I'm perfectly fine with the one on the left. The one on the right looks a lot better, doesn't it? We're going to have to figure out how we best draw. And that means that in a lot of cases, we're going to go and erase and put what's in front and what's in back. For those of you who have not seen it, I recommend you look up M.C. Escher's building, Belvedere. Because it's actually a physical building, right? It's a building, right?
Yes.
If you look at the building carefully, there are people standing at the end of the first floor and the end of the second floor. And one of them is looking this way. One of them is looking this way. They're doing the Necker cube. And he's even weirder. He's made the back look like this and the front go the other way. And in the bottom corner of that painting is a person holding an impossible cube. Because the cube they built looks like this. Ready? According to this piece is in front. According to this piece is in front. So the top point's one way, the bottom point's the other way. Ooh, that's weird. So drawing in 3 dimensions is a pain in the ass. On the other hand, I have a computer. And the computer will draw really well for me in 3D. I can plot 3-dimensional points a lot better on a computer than I can plot them by hand. So when it comes to drawing complicated stuff, we will not draw by hand. But looking at equations and figuring out whether or not I drew it correctly on the computer is going to take some work. More on that later, though. Questions? Okay. Let me think about some quote-unquote easy graphs. Ready? Here's a graph. I'm going to give you an equation in 3D. Now, in 2 dimensions, what's this the picture of? Y equals 2. A straight line. What kind of a line? There's another adjective I can use. Not just straight, because all lines are straight. Oh, it's horizontal, right? Y equals 2, a slope of 0. Okay, but in 3D, it's different. When we write y equals 2, we think of x as being allowed to be anything we want, yes? But if I think in 3D, not only is x allowed to be anything we want, so is z. Wait a minute. If I can have x be anything and I can have z be anything, then instead of having 1 degree of freedom, I have 2 degrees of freedom. There's the point y equals 2. 0, that's 0, 2, 0, right? On the y-axis. Let's draw that line. X is allowed to be anything it wants, right? If x is allowed to be anything it wants, I get a line like that, parallel to the x-axis, right? The x-axis would be down here, and the line y equals 2 would be up here. Perfectly parallel, both with slopes of 0. But z is also allowed to be anything we want, right? So that means from this point, I can go up or down Wait a minute. What have I described? Not described a line. I've described a plane. What I have here is a surface at 2. It's not tilted right. I can't lay it down here, right? It should be coming straight out at me, but it should be tilted to match the, oh, right, crap. Here. Here's my surface. Okay. So the definition horizontal doesn't work anymore. Because I think of that plane as being vertical, don't you? I mean, it's going this way, up and down. All right, maybe. That would be horizontal, but that's not a good description either because it's also going back and forth. What would that surface look like? It'd be under the floor at a height of -1, but it would be parallel to the floor. Like this surface, y=2, is parallel to the wall with the windows in it, moved into the room 2 units. This is moved under the floor 1 unit. So we have the xz plane. If I'm standing over there where y is 0 at the windows, I'm on the x-axis, I'm on the z-axis. The xz plane, y=2, is parallel to that. z=0 would be the xy plane, the floor. This is parallel down 1 unit. The board is the xz plane, y is equal to 0. So if I did x equals -5, we'd be in the room behind us, 5 units, but we'd be parallel to the wall here. So the coordinate planes become our walls. Again, a room, a person at the origin, and the 3 labeled planes. But what I've really described are sets. A surface is a set in 3 dimensions. Distance. I remember when I first learned about the Cartesian plane, we wrote out the distance formula. Remember the distance formula? Maybe. I want the distance d between point 1 and point 2. So we'll call this x1, y1, and we'll call this x2, y2, and I'm just doing it in 2 dimensions. How do I figure out how far it is from point 1 to point 2?
This one is x2 squared. And then y1, y2 squared.
I need some operations in there.
minus x2.
And y1 minus y2, and then a plus in the middle, because what we really did is we made a little right triangle. And this distance is the change in x, and this distance is the change in y. That's exactly, it's Pythagoras. Wonderful, beautiful, marvelous. I love it. How do I do it in 3D? It turns out to be explicitly generalizable. Pythagoras still works in 3D. It's a little hard to show with my crappy artwork, but the distance here is x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared, all square rooted. And on page 795 in our text, there's a better picture. So let me stick that up here for a second. I'll zoom in, blow this picture up a bit. Notice the first thing they do is they do flat. Here is the two-dimensional Pythagorean distance, right? Then I have another right triangle that's flat. But this is already a square root, so when I square it again, I get x1 minus x2 squared plus y1 minus y2 squared. And then I do this, which is z2 minus z1, or z1 minus z2 squared. I add those together in square root. So it turns out to be exactly generalizable, precisely how we want. And the distance formula in 2 dimensions is exactly the same as the distance formula in 3 dimensions, with one extra letter. And this is what I mean by Calc 3 is Calc 1 with more stuff. It's the exact same formula, just add another letter. I like this. For those of you who have seen or done a linear algebra course, this is the Euclidean distance, this is the dot product distance, this is the same norm we use there too. It works in any number of dimensions we want. I'm not going to do it in more than 3 in this course, but we could. Questions? This formula will come back repeatedly throughout the semester. Put a star on this one, we're going to need it. All right. I remember distinctly in my algebra class, right after I talked about the distance formula, I talked about circles. So here's a question for you. What's the equation of a circle? In x and y. Don't worry about z at the moment. Let's do a circle in 2D. That one has the center at the origin. And if the center is somewhere else, I need to shift x and y to make up for that, right? So in 2 dimensions, if I say, oh, let's write x squared plus y squared equals 4. What am I describing?
Circle the origin with the radius of 2.
Great. Circle at the origin with radius 2. For a second, that's coming through the shoe alert. Those of you on your email, please check your alerts right now. There is a police event near campus, so we're not leaving this room until they go clear. Advantage number 1. This door does lock. If we hear weird shit, come to this corner. It's safest and won't be visible from the door. These are cinder block walls. Okay, that's in 2D. I'm going to keep going because I only have 10 minutes and I really want to get through this, I promise. What if I do this same question in 3D? What happens in 3D? Think about our plane. What did we say was allowed to change when we moved from 2D to 3D? What did we say was allowed to change when we moved from 2D to 3D? We thought about our line versus our plane.
The circle just came to a sphere.
Okay, wait a second. In this, we took the line and then we said that z could be anything we wanted. If I take this circle and say that z can be anything I want, what does that do? It doesn't make a ball. It moves that circle up and down and makes a cylinder. So I have a free variable, the ability to say, oh, z can be anything I want. I get a circle at any height. And that means I have infinitely many circles stacked up one on top of the other. That is a cylinder. But you said sphere. Let me think about sphere for a minute. A sphere is like a circle moved to 3D, right? I think of that as distance, because a circle is the set of points that are the same distance from my center. But now I want that distance to allow myself into 3D, right? So instead of using the distance formula in 2 dimensions, I'm going to use the distance formula in 3 dimensions. If I want a sphere, I want points that are the same distance from my center. Now my center used to be HK. I need a 3D center, so I need another letter. I'll call it L. So now I set up my distance formula. And I square everything so I don't have to deal with the square root. So I get x minus h squared, y minus k squared, and then I get z minus L squared. And there's my radius on the end, r squared. Just like a circle with one extra letter. Okay. I like this. This is good. Problem. Just like we did with circles, I may have to do completing the square to make this look like a circle. And if I have to do completing the square, I'm going to have to do it in all three variables. So instead of just doing it once, I'm just going to do it not twice. I'm going to end up doing it 3 times. So my big problem is that if I say, oh, I've got a circle. Ready? Here's my circle. Sorry, a sphere. X squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0. That's a sphere? Sure it is. Well, the way to check is to rewrite it so it looks like this. Let's find the center. Let's find the radius. Text message just came through on the all clear, so we are able to dismiss class when time occurs. Whew. I'm going to regroup, put the x's together, leave a space, put the y's together, leave a space, put the z's together, leave a space, put the 6 on the other side just to get rid of it for now. And now, complete my square. What's the appropriate thing to add in the x's to complete the square?
X plus C squared.
Right, but that would mean what do I put here?
No.
I put it's a plus, not a minus, because that's a plus and I'm squaring, so it becomes, but if I add 4 on that side, I have to add it on this side. What do I add here? Plus 9, same thing over there, and here, plus 1, same thing over here. How'd you get those numbers?
Coefficient of the second term.
And then square. So we end up with x plus 2 squared, y minus 3 squared, z plus 1 squared, and over here, 14 minus 6 is 8. So I have a center. Remember, these are all minus signs in my formula, so my center switches signs, and my radius is the square root of the other side. This is a circle. Yay. Sorry, a sphere. Now, I'm in 3D. What if I want a ball, not just the surface? Because that equal sign makes this the skin of the surface of the sphere. If I want to talk about everything inside the sphere, then I need to say that I want all the points whose distance is less than or equal to 8. And if I want all the points outside the sphere, I'm going to say bigger than or equal to 8. If I only want the top or the bottom of this sphere, I may say only let z be bigger than 0. Maybe I want the left half, only let y be bigger than 0. I can now build in sets to define regions in space, inside of something, the outside of something. I can talk about moving from the inside to the outside. Ladies and gentlemen, I gave you dispersion across a semi-permeable membrane, osmotic pressure, diffusion reactions. There's a lot of stuff here. Okay. In general, I'm going to do my work in 3D. But a lot of what I'm going to do is going to look like limits and derivatives and integrals. But I've got to figure out how to move those up here. We're going to spend a lot of time working in vectors in 3D. So this is our framework where we hang everything. We'll just keep going from here. All right? I will see you all tomorrow. Same place, 1 o'clock.